Welcome in, everybody. My name is Christine Anderson. I am the president of Astronomy Club. Tonight, we will be having a presentation by Martin Mattis. Please tell me if I said that wrong, because I've been saying it wrong for a very long time then.
You got that right.
Yay.
Hello, everyone.
So, Martin, if you would like to give a quick brief on what you'll be presenting on tonight, I will let you get started.
Yeah, so background, in 2019 at the American Physical Society April meeting, I was in attendance and I got to hear one of the first press releases of the Event Horizon Telescope's publishing of their image of a black hole. And so that was something that was really exciting from that experience, and I wanted to share a little bit about what I learned there with you all here. So without further ado, I will start sharing the presentation. So like I said, my name is Martin Mattis, and Christine, you did get that pronunciation correct. And I'm going to be talking a little bit about the Event Horizon Telescope. So back in 2019, like I said, in April, this image was released from a team that called themselves the Event Horizon Telescope. And I'm going to talk a little bit about what you're looking at here, and then go into a little bit of detail about how we got this picture, and then talk a little bit about what's next for the team. So we're looking at the galactic core of M87. M87 is a galaxy that is located in Virgo. So here's the constellation Virgo, and right up in the corner here, you can see there's a cluster of galaxies, and M87 is right near the center of all of them. And it's a large elliptical galaxy, and it's about 53.5 million light years away from where we call home here on Earth. So I'm going to do a quick video here that shows a zoom in to the center of M87 here. So that's the galaxy M87, and you can see its elliptical shape there in the visible light. And as we switch into the X-ray, you can see some different structures through it. And one of the interesting features of M87 that scientists have been studying is this plasma jet that is shooting off to the lower right. And that plasma jet is what kind of got scientists thinking that maybe there's a black hole that we could see in this galaxy. And so as we built larger and larger telescopes to get higher resolution images of the core of M87, you can see we kept getting closer and closer to the source of this jet until eventually in 2017 was when the Event Horizon Telescope was actually taking its data, and they were able to resolve this small space right at the center of M87, which is the event horizon of the supermassive black hole there. And so looking at this picture, it's a little blurry because it's a very far distance away, and it's a relatively small field of view for how far away it is. But it's the galactic core, like I said. So everything in M87, the galaxy, is orbiting around this object. And we believe this object to be a supermassive black hole. That classification comes from it being 6.4 billion solar masses. We estimate it to contain about 6.4 billion times the mass that our sun here has. And so when you're looking at the picture here, there's the shadow in the center, which is the exciting feature of the picture. And it's about 350 astronomical units across. An astronomical unit is the distance from Earth to the sun. And so 350 times the distance from Earth to the sun is the diameter of this shadow that we're seeing from the supermassive black hole. And so the bright edges around it is the accretion disk from the matter that is falling into the black hole. So looking at what we might be able to see if we're able to get even higher resolution on this area, this is a simulation that some scientists put together using what's called magnetohydrodynamics. Essentially, it's a fancy way of saying they're looking at the magnetic field lines and how they flow like a fluid around the black hole due to the high changes in space-time that are happening in the large gravity there. And you'll notice that there's a bright spot off to one edge, and then the other side of that is very dark. And this is from what's called Doppler beaming. It's very similar to when you hear an ambulance driving down the street towards you, and it's a higher pitch sound and louder as it's driving towards you, and then it gets quieter and lower pitch as it's driving away from you. That's what we're seeing happening here. As the matter that's falling into the black hole is releasing light, when it's spinning towards us, its light is getting shorter in wavelength, and we're able to see more of it. As the matter is moving away from us, we're able to see less of that light, and it's at longer wavelengths. And so that's where that bright edge comes from in the image that we're seeing. As we zoom out a little bit, where is that light coming from? It's from what's called an accretion disk. So I have here an artistic rendition of what an accretion disk might look like if we were able to get a high enough resolution picture of it. And you can see here, it's kind of donut shaped, and it's a very turbulent area of space. So there's lots of different flows of where the matter is trying to go and being pulled in different directions. But mostly it's being pulled down towards the black hole. And the main force that's pulling it in is actually friction. So if it was just gravity acting on it, then the matter would be able to orbit the black hole like our planet orbits the sun. But because there's so much matter concentrated around the black hole here, it hits all the other matter and eventually loses energy as the friction turns that energy into heat energy and light energy. And if you remember from maybe high school physics class or introductory physics class, your energy is equal to your mass times your height times the gravitational constant. And so if this diameter here is 300 AU, we're looking at thousands of 1,000 AU of energy that you have to burn off before you can fall into the black hole. And so all of that energy is being released as the light that we see. And that's what causes the bright edges to the black hole that we're able to actually take a picture of. So how do we take that picture? Now that we know what we're looking at, it's with a telescope, but not the type of telescope you're probably used to seeing or thinking about. The specific wavelength of light that they're looking at is in the millimeter wavelength, so that they can see through a lot of the accretion disk and even the radioed plasma jet that is shooting off the side of the black hole. To be able to see past all of that, we need to look in a very short wavelength, and it happens to be radio dish telescopes that look like this that are able to detect the millimeter wavelengths of light that allow us to take this image. Now, this one telescope that I have pictured here, the resolving power of it isn't high enough to be able to make out the structure of the black hole. So we need to get a lot of them. And having a whole bunch of them in one area is useful, but if we're able to spread them out all over the world, we can increase our resolving power even further. And so to talk a little bit about how we do that, oh, and before I do that, we're also able to increase the amount of area that we're collecting as the Earth spins. So if we record for 4 or 8 hours, we're able to cover large swaths of area through our telescope as each of our individual dishes rotates through the Earth about the Earth's axis. And then we get to fill in different spots in the image that we're trying to take. Now, if you look at this image here, which is kind of a depiction of the effective resolving locations of all of our telescopes that go into the Event Horizon Telescope, you'll notice that there are a lot of gaps. And so to fill in those gaps, we use a process called interferometry. So through interferometry, we're able to use the fact that we know we're looking at the same light source at multiple different locations on multiple telescopes at the same time. And if we know the distance between those telescopes, we then know the difference in how far the light had to travel. So we're able to synchronize all of the light that we're collecting at all of our different telescopes. And then using some math, we can fill in all those gaps in between the telescopes with what we should be seeing. So here's a nice graphic that I was able to get from the Event Horizon Telescope's website that kind of shows how you can increase your resolving power by adding more telescopes using this interferometric system, and then including the Earth's rotation and even looking at different frequencies of light. You're able to increase your resolution even further. So you see at the beginning of the animation, they start with 2 telescopes and you just kind of get this fringe pattern across the sky because that's all the information you can really get if you have 2-point sources of information that you're looking at. And as you increase telescopes, you're able to reduce the possible sources of light. And then as you spin them around, like you're spinning about the Earth's axis, it covers in the different areas that are between the telescopes, and then adding different frequencies that you look over kind of smooths out the final details of your image. So from that, using all of the telescopes that collaborated for the Event Horizon Telescope, we're able to get an effective dish size that is on the order of the size of the Earth. And so we're able to fill in the details, even though we don't have any telescopes out over in the oceans here. We're able to fill in those details by using the math from interferometry to extrapolate what we should be able to see there. The effective resolving power of the Event Horizon Telescope, if we were able to set it up in New York, we would be able to read quarters, like the date on a quarter, if the quarter was over in LA. And that's some crazy magnification. So through April 5th, 6th, 10th, and 11th in 2017, about 5 petabytes of data was collected from M87 through the Event Horizon Telescope network. So each individual location on the network recorded about 8 hours of time on all 4 days. Due to some weather, the 10th didn't have as much data collected as the rest of the days, but in all, there is about 5 petabytes of data. To transport all that data, they actually had to ship it on the hard drives, which you can see pictured on the side here, because it was faster than sending it over the internet. And once they had all of the data collected, they made 4 copies of it and sent it off to 4 independent teams. The teams were not allowed to communicate with each other about anything relating to the data analysis. And that's to help prevent some confirmation biases from entering into the analysis of the data. So once the 4 teams got the data, they were told, tell us what this is a picture of. And 7 weeks later, each team returned using some different methods to analyze the data and try to create an image from it. And you can see here the results of that first 7 weeks. And the preliminary results were very promising. As you can see, there's a clear ring structure to all of the images here. And so you could convince yourself that that is the shadow of the black hole that you're looking at there. And you all have the southern bright spot in those images as well. So those features, this dark spot in the middle and the bright spot on the lower edge and the brighter ring around the shadow, seemed to be a feature of the data and not of any independent method of analyzing the data. So now that we know that we've probably looked at a black hole and taken a picture of it, we want to optimize that. We want to create the best picture that we can from the data that we collected. And so they did a whole bunch of synthetic data analyses, which is essentially they took the signature features of the data that they collected from N87 and tried to recreate what possible different sources of that light could look like. So they have an even brightness ring, a kind of crescent shape, which is what they're expecting to see, the disk, which is just even if it was a single point source of light, and then maybe a binary source of light as well. And so when they created this synthetic data, they overlaid different filters on it to make it more similar to the conditions near the event horizon, like the giant plasma jet that was obscuring some of it was overlaid on top of that. And then they simulated collecting that data through the telescopes that they had. Once they had that simulated data, they then ran it through the different algorithms. So they had 3 different prominent algorithms that they were using at this point to see what they would have gotten had this been the initial source. And so here you can see they added in a hydrodynamic model as well into the synthetic data. And from that, you can see the 3 different models here and what it would have looked like had this been the source. And so from that, they're able to optimize the parameters of each of the models to make the closest representation to the actual image that they were putting in to it. And to remove confirmation biases, when they were running a specific model through an algorithm, they optimized the parameters assuming that they were looking at different types of objects. So if they were looking at the ring, then they assumed that they weren't looking at a ring and optimized the parameters for these other 4 shapes, and then used those parameters to image the ring. So this is kind of like a worst case scenario of, all right, we didn't look at what we were thinking we were looking at. What's the worst case scenario of what we would see through our telescope when we ran it through our algorithms to create the images? And that's the results that they had from that. And then they used those optimized parameters to put all 4 days data through and get the best images possible from the different days in the different algorithms. And you can see here the results of all 3 algorithms over all 4 days. And every single one has the prominent bright spot, mostly to the south. And if you look between the different days, between April 5th and 6th, it's slightly more left than the April 10th and April 11th data. So that seems to show that the actual disk is changing over time and we're seeing it shift back and forth, potentially even rotating around the black hole where that bright accretion spot is from the Doppler beaming. And so now that we have kind of like a best fit from each of our different algorithms, we're able to take an average of those over each of the days to get our corresponding images of the M87 galactic core on April 5th, April 6th, April 10th, and April 11th. And so that is where the image from the Event Horizon Telescope came from, and how we were able to work from just a scattering of telescopes across Earth and combining all the data that they were able to take into this image that we have now. So moving forward, the team was able to go back and look at data from as far back as 2009 that was complete enough that they were able to use the now known assumption of the shape to reconstruct where that bright spot was over different years. So we can see here an animation from 2009 to 2017 showing how that disk where the bright spot is changing over time. And so we have a fun little movie now of the black hole and the accretion disk spinning around it. Moving forward, there is plans to look a lot closer to home. So M87 was millions of light years away from us. Now the team is looking at Sagittarius A star, which is the galactic core of the Milky Way. And so the predictions show that the event horizon should be a similar apparent size to the black hole that we were imaging in M87. And so we should be able to resolve an event horizon of Sagittarius A star. And there are plans to add more telescopes to the array of the Event Horizon Telescope that will enable us to get even higher resolution images from it. So hopefully in the future, we might even be able to see our own galactic core soon. And here we have an animation of the stars that are orbiting Sagittarius A star, which is marked by the star in the center here. Hopefully we'll be able to add an image to where that star is in the future. Thank you for listening. If you are interested in learning more about the Event Horizon Telescope, they have their webpage right here. And you can even look up the 6 independent articles that were written about the 2019 press release of information from the project. Most of the information here was pulled from the 4th of those articles, and they all have the same attribute here. The only difference will be the number after the L is which specific article you'll be looking at. And then the information about the video of of M87 came from a Nature article right here. Are there any questions?
This might be a far-fetched one, but what do you think the role of telescopes, say such as the James Webb, might have with helping image further black holes? What's the role of a mission, say, such as that one?
Yeah, so that's a good question. I believe the James Webb Telescope is designed for optical wavelengths. Correct me if I'm wrong there, but so that telescope will be helping us resolve things in the optical spectrum. As far as I'm aware, though, let's see, what is Dr. Foster? Oh, it's mostly IR. So yeah, let's see if I can move the chat box so it's not blocking the screen as much. Yeah, essentially, if you have enough telescopes in a certain wavelength of light spread over large enough distances, then you can use interferometric techniques with them. So if we have telescopes in orbit, that does increase our resolution. We're able to see smaller details. The further apart the telescopes are, the smaller details you're able to get. It's not as simple as that because you do need to have intermediate telescopes so you get different baseline lengths, so you can kind of build up iteratively from large structures with a couple of very close telescopes together to very small structures with telescopes that are farther apart. Any other questions?
Barring there being any other questions or comments, I would guess that we are done for the night. I don't have a bunch of fun conversation things lined up like Deanna would last quarter. I will work on making a change to that. But that was a wonderful presentation, Martin. Thank you so much for giving it.
Yeah, thank you for hosting me to the Astronomy Club at Central Washington University. And I'll definitely send them the presentation that I have here so they can archive that with whatever resources they send out.
Thank you. I'm going to go ahead and stop recording.